Hi everybody, it's CM Science and Math Tutor, and today we are going to be introducing the concept of waves. Mechanical waves and non-mechanical waves are similar in a sense that they both are defined by their ability to do work. However, they are different in many ways. Mechanical waves are waves that require a medium for the transfer of their energy to occur. And some examples of mechanical waves are first, water, seismic waves, and sound waves. All of these travel through a medium. For example, sound might travel through air or even solids like a door. They do not travel through vacuums, which is the reason they are mechanical waves. Non-mechanical waves are waves that do not require a medium for the transfer of energy to occur. An example of this is the electromagnetic spectrum. You're probably a little familiar with this, but AP Physics 1 doesn't elaborate on the electromagnetic spectrum. There are gamma rays, X-rays, ultraviolet rays, along with the entire visible light spectrum, infrared waves, microwave, and radio waves. All of these travel through a vacuum, which is why they are non-mechanical. I'm going to talk about pulse versus continuous and periodic. So pulse refers to a one-time disturbance. An example of this might be if you and your friend are both holding one end of a string and you move your arm up and down just one time, and one ripple gets sent through and it travels all the way down to your friend. This only occurs one time. It's just a single disturbance. That would be an example of pulse. A wave usually refers to a continuous disturbance, and periodic means it occurs at repeated intervals. So again, if you and your friend are holding a string, and instead of moving it up and down one time, you constantly move it up and down. This would be an example of a continuous or periodic wave. A traveling wave is a wave that is seen to move or progress across a certain medium. And this type of wave will definitely move. It consists of one wave which moves in a specific direction. It does transmit energy and all particles of it vibrate. So I'm going to give you an example of what a traveling wave will look like. All the particles of it are vibrating and transmitting energy and is moving in one direction. Next we have a standing wave, and a standing wave is a stationary wave. It will not move, and it's a combination of two waves which move in opposite directions. It stores energy, and it consists of nodes and antinodes. So I'm going to draw out an example of what this would look like if we had one wave that way and we had another wave this way. Then this section up here would be the antinodes. And right here would be the nodes. Now we're going to talk about the difference between transverse waves and longitudinal waves. Transverse waves are always characterized by a particle motion being perpendicular to wave motion. Transverse waves are waves that you are most likely familiar with and have talked about in previous science courses. In transverse waves, the source moves up and down and the coils move up and down, which is different from longitudinal waves. A longitudinal wave is a wave in which particles of the medium move in a direction parallel to the direction that the wave moves. So say we have a slinky, and instead of moving it up and down like a hand in a string, we are moving it left and right. It would have regions that are very stretched, and it would also have regions that are very, very compressed. And that is what a longitudinal wave would look like. Next, we're going to talk about some basic properties of transverse waves. So, say we have an x-axis and a y-axis. It's important that you note that we do not have time on the y-axis. We have two distances. If we were to have time where the y is, that would be a graph of an oscillation, not a wave, which is very easy to mix up. So say we have a transverse wave, just like we talked about on the previous slide. We are going to label some of the properties and characteristics of this. So the amplitude is this distance here. It is half the distance between the crest and the trough. And if you don't know what a crest and a trough is, that's okay. We're just about to talk about that. The crest refers to this and the trough refers to the point down here. It's at the bottom. Now the wavelength is the distance from trough to trough or from crest to crest. And wavelength is oftentimes refers to by lambda, which is a Greek symbol. And you might be thinking back to the oscillation unit when this distance right here, the distance from between two of the crest in this case, and you might be thinking that it's supposed to refer to a period, which is another thing you can get mixed up with oscillations. When we do have time on the y-axis, the wavelength on this graph would be the period on the other graph. But in this case, when there is a y, it's a distance on the y-axis. This is the wavelength. And again, if you were to have time on in the y-axis, that would be the period. The interesting thing about this is that you actually cannot get the frequency or the period from a simple picture of a wave. You could if you had a picture of an oscillation, but not if you had a picture of a wave.